So, the fundamental difference between an emission spectrometry and absorption spectrometry may be defined, we can define it like this: for emission to occur, a number of atoms must be in the excited state. I want you to understand when an emission occurs, when an absorption occurs. If I have lot of atoms in atoms at the excited state, just like in sun's atmosphere, solar atmosphere, then the emission can occur when those atoms at higher energy level come down to the ground level. For that, a number of atoms must be in the excited state, then only you can see some amount of darkness, is not it? Whenever they emit, a certain amount of energy is lost and that energy is available, and for atomic absorption to occur, lot of atoms must be in the ground state. The opposite also should be true. So, what we are saying is, for emission to occur, I must have a lot of atoms at the higher energy level. For absorption to occur, I must have a lot of atoms in the ground state. So, from ground state, absorb energy goes to the higher energy state. From higher energy state, emits the radiation, comes down to the ground state. So, which is more easier? I want to pose you a question: which is more easier, to have atoms in the ground state or at the excited state? In normal circumstances, ponder over this. There is a lot of energy around us, electromagnetic radiation is available, but all of it will not be absorbed by the atoms from the objects around us, but because it has to be quantized. Only the quantized amount of energy is able to absorb, right. So, the maximum number of atoms in a given system, if I am not supplying any additional energy, would be in the ground state. If I supply energy, they will be in the higher energy level. So, the second condition is usually attained compared to the former, that is, electrons will be in the ground state. That means, free atoms in the ground state can be easily generated in the flame compared to the excited state by flame emission. I do not know how to say this. For atomic absorption and emission to occur, it will not occur in a material which is which I am holding here. For example, there is a metal tip here. The atoms in this metal tip are not free atoms. They are not free to move. They are all fixed in a matrix. If I take any metal or a keychain, for example, I have a keychain here and this keychain is made of steel. That means, iron atoms are there, maybe some chromium, manganese, etc. they are all there, right. So, the atoms in this keychain are not ready to absorb the radiation because they are all bound, electrically neutral. The radiation around me is not enough to absorb the radiation for the atoms to promote them to the next higher energy level. This is what I was trying to tell you since last 5-10 minutes. What it means is, most of the atoms in the at room temperature are bound, they are not free atoms. If I have a free atom, then it can absorb or emit radiation. Now, how do I generate a free atom in the laboratory? Even if I give you this keychain, you may not be able to generate free atoms from this keychain. For that what I do is the free atoms I have to generate from a system which is to be melted and vaporized. Okay. So, that is the trick I will have to employ. I have to find out how I can make a substance melt, vaporize, the atoms will be there in the vapor state. Even then the atom will be in the neutral they will be in the ground state. They will not be even in the vapor form. If I take for example mercury, you take mercury is liquid at room temperature, right. So, if I heat mercury it will boil and then it will become vapor. Similarly, if I take lead around 200-300 degrees, if I heat, lead will become liquid and then it will start vaporizing. Sodium around 1000 degrees, like that they form vapors in the given atmosphere. And in the vapors also electrons are there in the ground state, not at excited state. Atoms, I mean atoms are in the ground state, because the radiation around it is not quantized. So, it is free atoms I can generate by heating it in the flame, and in the flame if the concentration increases etc., they can emit radiation also. For example, you must have studied in your high school level that or college level that if you take sodium metal and burn it in the air, it gives out yellow light. Put it in a flame, it will give yellow light. If you take potassium, it will give a violet light. So, that is emission. Because, but if there is not, that means there are lot of potassium atoms in the flame which can get excited and emit the radiation when they come back. So, in the flame I have atoms in the ground state which can be excited to higher energy levels, and if the higher energy level is attained without emission, then it is absorption, and once the higher energy level atoms come down to the ground state, then it emits radiation. That is how we see. So, yellow light from sodium and then red light from potassium etc. You just study your flame test for in qualitative analysis in your college levels, you will see that there are number of elements which will give characteristic emission lights in the flame. That is known as borax bead test. If any of you have the remember, I suggest you take a look. So, what we are saying essentially is you take a metal system, heat it, convert it into vapor state, and in the vapor state you will see that atoms are in the ground state. There are very few elements in the periodic table which have higher concentration in the flame, in the vapor state. In a flame they are sodium, potassium etc., they emit the light. So, both emission and absorption occur in the flames. So, if you understand this much, we will proceed to the next slide. So, the next slide is, can we determine the characteristic wavelength for an atom once the energy levels are experimentally determined. I have shown you Gaussian diagram. In the Gaussian diagram I had shown you that different energy levels are there, were determined by the lines. I had shown you that corresponding to particular frequency and particular wavelength. So, the characteristic wavelength, that is resonance wavelength for an atom can be calculated once we know the energy, but several wavelengths are not observed at all. It is not that you will see every line in a spectrum whenever you take a spectrum, some of them are not observed, which proves that there is some sort of selection rules are there which permit a particular transition and which forbid particular transition. So, these rules were evolved empirically at first by looking at number of spectrums which particular frequency line appeared, which did not appear, like that, and subsequently they were confirmed by applying quantum mechanical principles to the concept of transition probabilities. Okay. So, the possibility of a spontaneous emission by transition between energy levels and E1 and E2, what I am saying is possibility of transition. Now, we are talking about the probabilities. So, the probability of transferring from one energy level to another energy level is defined as the number of atoms that are in the ground state and to the higher energy state. So, the fraction of number of atoms that drop to the lower level per unit time, of course, we have to introduce a parameter known as unit time. So, with this unit time we can determine the probability of a spontaneous emission like sodium and potassium. Okay. Mathematically what I do is I write an expression something like this: dn, this is the probability, 1:2 is the transition, that is AN1, A is the coefficient of proportionality termed as Einstein emission coefficient. Higher the probability of transition, the greater is the intensity of emission. The strongest emission lines correspond to values of A in the range of 10 raised to 8 to 10 raised to 9 per second. What I am going to teach you now is to derive an expression for the spontaneous probability of transition from one level to another level, that is level 1 and 2. I am going to derive a small expression, mathematical expression, and this you will not find in any textbooks, but this is the fundamental basis of all atomic absorption. Try to understand. It is not very important that to become a good analytical scientist you must understand this, but if you are aware of this, it makes lot of difference to your scientific career. So, what I am saying is try to understand the derivation, at least the logic behind it, and then we will see how we can quantify the emission or absorption. So, what we are saying is the dn, the transition 1:2 is a function of Einstein emission coefficient multiplied by the number of atoms there and with respect to time, and the time range is 10 raised to 8 to 10 raised to 9. So, similarly, if N2 number of atoms in the lower transition state are at the lower energy state are irradiated by a transition frequency, that is quantum mechanized frequency mu derived from equation 1, and the volume flux density is rho v, the number of d atoms N2 to 1 atoms that will absorb the radiation in time dt is proportional to N2, rho v and dt. These are the three parameters, one is flux, another is number of atoms, and t is the time fraction. So, I am going to write dn2 to 1 is equal to b2 to 1, that is another proportionality constant, and n2 is the number of atoms and rho v is the flux. So, what do we mean by flux? The total number of atoms in a given space. Okay. So, the B2 to 1 is known as Einstein absorption coefficient. Earlier we had written a similar expression as emission coefficient. Okay. So, now I am going to introduce why this is from 1 to 2 and from 2 to 1 it is known as absorption. So, it is essentially the same thing, quantification. Higher to a higher energy level, lower energy level, higher to lower is emission, lower to higher is absorption. So, nowadays what is important is the term if an electron is going up and down, up and down, up and down, we call it an oscillator. So, how many times it happens is known as oscillator strength. So, we used a term what is known as oscillator strength in all our expressions. The between B and the total number of atoms, and this can be quantified by this expression pi into E square into lambda divided by mass into Planck's constant into velocity of light and frequency, okay, where E and m are the electronic charge and mass. Here this is E and this is m. For sodium D lines, oscillator strength is 0.23. If I put all these numbers for sodium, it is I get a number what is known as what is approximately 0.23 and 0.47 for two resonance lines, and for potassium they are 0.35 and 0.70. Okay. So, oscillator strength is an important parameter in atomic absorption spectrometry. It does not appear in your day to day analysis or anything like that, but still it is a parameter to be known. So, the emission lifetime of any transition is approximately 10 raised to minus 8 seconds. This I have also told you in the spectrophotometric course in NPTEL that 10 raised to minus 8 is the emission lifetime of any transition. So, if there are sufficient number of atoms, steady state emission or absorption, there will be an equilibrium between absorption and emission, absorption and emission. So, this steady state absorption phenomena can be observed within the experimental time frame. So, say within a few minutes, a few seconds, etc. After some time you will not see any change, it will remain steady because it will be in equilibrium state. So, for atomic absorption to occur, intense emission of the desired element must be generated first. That means, the I have to provide radiation which is to be absorbed by the free atoms. So, I need to provide intense emission of the corresponding wavelength energy electromagnetic radiation of the resonance value. Whatever is the resonance wavelength, I have to produce radiation of that wavelength in very high intensity. You get it? So, high intensity of the same wavelength, that is resonance wavelength, that we have to generate first. So, the radiations generated from electric dipole, magnetic dipole, electric quadrupole interactions give rise to such lines, among which electrical dipole is the most important. What we mean to say in this is, how do I produce an intense radiation corresponding to one particular wavelength for sodium, that is 589. How am I going to produce? So, there are three methods. One is electrical dipole, magnetic dipole and electrical quadrupole interactions. So, how do I generate this thing? Using electrical dipole is the best way. So, both Einstein emission and absorption coefficients are non-zero only if the levels involved are of opposite parity and if delta j, that is the difference between the two, is plus or minus 1. That means the energy level must be in resonance. Okay. So, under this using the selection, this is one of the selection rule only, if delta j is plus or minus 1. So, if it is plus or minus 2, definitely it will not work. So, using such selection rules which are available from the literature, resonance level of an atom may be determined, of any element for that matter, may be determined as that of the lowest excited energy level that can interact with the ground state by a transition of electrical dipole type. So, what we are saying is, with an electrical dipole type, given a selection rule, the resonance line of any element can be determined. That means, we have number of data which can already in our computer, in our database, in our Google or whatever it is, the resonance levels of the energy of almost all the elements of the periodic table. They are already calculated and available, information is available to us, and the corresponding wavelength is known as resonance line. So, this you should understand. So, it is very common practice in most of the atomic absorption spectrometers. What is a resonance line? So, so many times you will come across a technical term, the resonance line of iron is so much, the resonance line of chromium, copper is 324 per 2.7, like that. So, what you will understand by that? We mean that the lowest energy level corresponding to the transition is a resonance line. Therefore, it follows that a particular atom, for a particular atom, the resonance line is the most intense line. That is why we have shown it as a thick line. So, that is the highest oscillator strength, and only this line is useful for analysis, provided the wavelengths are in the 200 to 600 nanometer range. The resonance line must be 200 to 600 nanometer range, that covers UV and visible range. Thank you. We will continue our class in the next meeting.